Thanks, guys. So just to give you an overview of what we are going to cover today. So we're going to talk about some of the, give an overview of multi-cluster architectures and the problems around scale that they attempt to solve. We will start with a couple of reference architectures. Our hope is that you take this back and are able to apply some of these reference architectures in unique ways and talk to us about it. We're also going to take a behind-the-scenes look at what enables multi-cluster architectures. At that point, we are going to segue into Alcuin. He's going to talk about GE Aerospace's journey. GE Aerospace moved from on-premise to AWS almost 3 years ago and has been an amazing partner here through the journey, giving us feedback and really scaling to new heights. So Alcuin's going to cover that. And in the end, Anusha is going to bring it all together with an excellent demo she has prepared for this session, and also give you some best practices and steps how you can go from a single cluster to multi-cluster. We'll leave 10 minutes in the end for Q&A. We'll also be happy to hang around after the session if there are more questions. Speaking of questions, how many folks here are already using Redshift? OK, most of you. And how many folks are using a single cluster architecture? OK, a few of you. This side is single cluster. So we have multi-cluster experts on this side of the room, which will make the question and answer session interesting. Please do share your words of wisdom. So let's jump right in. So here's a common pattern of a single cluster architecture. And often as your warehouse journey starts out, you may have different workloads that are sharing a single compute. And here's an example where you see 2 write workloads. You see a streaming ingestion and batch ingestion that's happening on the compute. And then you have a bunch of consumer, your reporting, BI, science workloads. And up to a point, you can scale. You can scale vertically. You can scale horizontally to a certain point. However, at the end of the day, when you have multiple workloads that are running, there can be interference between workloads. Why? Because behind the scenes, it's still the same CPU, same network, I/O, and I don't know, some of you may have experienced a user that forgets to add a timestamp predicate or runs a Cartesian join without specifying a join clause. And this sort of interference, the blast radius is huge. So because what this can do is end up consuming a lot of resources and start impacting your other critical reports. And let's face it, we don't want our ingestion jobs to be impacted because downstream reporting depends on it and so on. So what's the solution here with multi-cluster? So you see this big hexagon, which represents that single compute, a large compute. We basically break it up into multiple different endpoints. And what you see here is, you remember there were 2 write workloads, so streaming ingestion and batch ingestion. Those are now split and actually writing to the same tables or different tables within the database. And then at the bottom, you see the 3 different consumers, the science workloads. They all have their endpoints. The advantage now there is that you can size these endpoints based on the unique SLAs, the needs of that workload. And when you build architectures like this, you're not just building this for today, but you're building this. You want to make sure these are extensible for needs of tomorrow. And in this architecture, if you want to just add more compute, within seconds, you can actually spin up additional endpoints that are consuming the same shared data. We refer to this architecture as a hub and spoke. And the hub is basically referring to a centrally managed team that is doing the writes, and the spokes are the various consumers. Now, here you see there are, I guess, are there 2 hubs, the streaming writer and batch ingestion. As of last week, you could only have a single compute that could write to a given namespace. And what we announced last week was the ability for different computes to be able to write to the same data sets. Let's look at another architecture pattern. So this might represent like what you see in a typical large enterprises. Many orgs, silos, or departments, finance, sales, marketing, and all the different teams in this case are using the same large compute here. We see a couple of compromises that end up happening in this situation. Often the compute ends up being over-provisioned, which means you're trying to provision for the peak of the sum of all usage, and that means often higher costs. The other aspect is chargeback. In enterprises, there is often a requirement we hear from our customers to be able to charge back usage to finance, sales, and based on the compute that they are using. The other part is now here in this example, you see finance and R&D are using the same compute. For, say, Sarbanes-Oxley and other regulations, finance may have a 7-year data retention, while R&D doesn't need that much. But again, you end up being compromising to meet the needs of all and maybe have a longer retention for all your users. To overcome all of this, and you start seeing a pattern, that big hexagon breaking up into smaller parts, and you have, again, each department or team here having their own endpoint. In this case, the difference is each of them manages their own data. And they think of them as the data owners, and they decide which aspects of the data they want to share with others. And this is important. For example, human resources, there might be social security numbers or sensitive compensation data, which you don't want to share with sales or marketing, for example. So they govern what they should share, what they want to share. And the best part is you still can get a customer 360 view by having a unified view of the data across all these units. So if marketing is running a campaign based on sales data, they can still do that without doing any kind of data movement. So let's go a little behind the scenes to see what powers these multi-cluster architectures. So we talked about no data movement, no data copies. And one thing I would urge all of you is like any places where you're making multiple copies of your data for your analytics need, you inspect that closely because copies are hard to manage. They become out of sync. Governing them becomes a nightmare. So at the heart of a multi-cluster architecture is Redshift's managed storage layer, which is a highly optimized for analytics columnar storage layer. It has many different optimizations. The goal is to make analytics queries run very fast in a cost-effective manner. On the compute layer, we have a massively parallel compute, and you have two options there. You have a provisioned compute, where you pick, hey, I want these many nodes, this instance type, and so on. Or you can have a serverless. You can say, hey, I don't want to manage any of the infrastructure. I just want to have 32 RPUs. RPUs is Redshift's processing units. Think of it as a knob for compute needs. The good thing about this is now you can actually have a mix and match of serverless and provisioned compute based on your needs. And you can pick the compute size. So in this example, you have one compute that is consuming the same data using just 8 RPUs, while another compute is using 1024. So just think of that picture we showed a few seconds ago, where the batch ingestion, you want that to go as fast as possible. You may want to scale it up to 1024. The nice thing is with Amazon's intelligent scaling, you can just hey, set the scaling to auto, let Redshift figure out what the right size for my workload is. Another thing is all these compute layers, they don't need to be within the same AWS account. These can be across accounts, and where this can be beneficial is like maybe you have a partner team that have their own account separation, so you're not restricted to consuming the data from different accounts. Even better, you can actually consume the data from different regions. And this can sometimes be useful for, say, GDPR-like compliance, where data must stay within the region, within the country. And so you can have, for example, a serverless compute that is in EU reading data from that is stored in Virginia. One question we sometimes get at this point is, okay, so if one of these compute layers is doing a write, how long does it take for any of the additional compute to read? As soon as the writer commits, at that point, instantly, the compute, which could be in a different account or different region, is seeing the same transactionally consistent data. Redshift has the snapshot isolation, and is able to, so you're not compromising on any of the data freshness, which is important to a lot of your applications where you might be making, say, near real-time decisions. The other thing is in terms of multi-tenancy. So we have several customers who have multi-tenant architectures. You could, for your largest clients, you could just have an endpoint which you charge back to them, and it's for their, and tuned to their SLAs. So once again, you don't have to offer the same service to all your tenants. You can have different services with using this multi-cluster architecture. And once again, there is no data movement that you have to worry about in this case. So you heard me talk a few times about how great it is to query a single copy of the data, same copy of the data through different computes. Now, you may wonder, what about the governance, access control, permissioning? As you add additional compute layers, are you ending up replicating the permissions? And that becomes a hassle. And while you can do that, while you can have permissions for every compute, a lot of our customers want to just be able to scale easily and have a centralized governance layer. With Redshift and Glue Data Catalog, you can do exactly that. What you see on the left-hand side here is the data owners. So these data owners decide they want to share or publish the data with the Glue Data Catalog. Some of you may be familiar with the Glue Data Catalog. You use it to discover your external tables like Parquet, Iceberg, et cetera. You can now use the Glue Data Catalog to also discover your Redshift tables. Then using the lake formation access policies, at that point you can set your access controls. This could be at a table level, or column level, or even at a row level. So go back to our HR example where we had a social security number. You may want to set up a masking policy that only, only if it's a HR user, they can see the full social security number, but no one else should be able to. Or row-level policies where you can say, hey, within this table, based on the role in the organization, these are the subset of rows one can or cannot see. So you set these policies once, and you associate or grant these policies to a role. In this case, we have Jill. She is an analyst. And Jill happens to be so she could be an IAM user, or using Identity Center, you can federate to your corporate directory. So this could be your Okta, Ping Federate, Active Directory, and so on. So that's your identity and the role you belong to. And then you have policies based on the roles. So say if Jill moves from analyst role to something else, somewhere else, you don't have to rejiggle all the permissions and struggle with that. At this point, when Jill logs on to any of the consumers, and this could be a Redshift consumer, and as of yesterday, the consumer here could be Athena, EMR, Glue. This is part of our SageMaker Lakehouse, where the data can be accessed from any of the engines, including Redshift data. Jill authenticates, again, using the same identity. And the catalog figures out what permissions, what access controls Jill has. Now, at this point, as you add more consumers, your central governance stays intact and just making sure your auditability and policies are all in one place. So just a combination of central access control and no data movement makes it really easy for you to set up multi-cluster architectures. Let's now take a look at a real-life example from Alcuin as he walks through GE Aerospace's journey.
All right. Thank you, Naresh. I appreciate the chance to be on here on the stage and tell our story. My name is Alcuin Whitus. I'm a senior principal data architect for GE Aerospace. And what I'm going to do and what I'm going to walk through here with you all today, I'm going to tell you a little bit about our business, but then I'm going to get into our Redshift specific journey, and we're going to highlight the ways that we've scaled with Redshift and the way we've taken advantage of several of those multi-cluster strategies that Naresh laid out there previously. So to start off and to cover our business and who we are at GE Aerospace, I absolutely love to begin with our purpose statement. So we invent the future of flight, we lift people up, and we bring them home safely. Those are very simple words, but extremely profound. And what they do is they embody the deep sense of responsibility that myself and every other employee at GE Aerospace carries with them day to day in the work that we do. Now, how we look as a business, we are a world-class leading provider of jet engine aircraft, or jet engines, as well as connected systems and other components on the aircraft. So when you think of GE Aerospace, we are all over the airplane, not just the engine, but in many other ways as well. And from a company standpoint, we have a deep history of innovation. So we have decades of innovation where we were not only innovating on our products, but pushing the entire industry forward. And that also translates to forward-looking goals as well. So we have aspirational and future-looking goals around things like net zero flight. So not only did we push the industry from a standpoint of decades of innovation, we'll continue to push the innovation and the industry forward through some of these aspirational goals as well. Now, since this is a Redshift session, I absolutely love to present our business in the form of a data slide here. Most of us in the audience are data people. And with this, I'll steal a quick move from Naresh and ask you to raise your hand if you flew on an airplane to get to reInvent this week. All right, myself included. So looking around the room, that was most of us. And what that means is flying connects us. Flying connects us to each and every one of each other here in the room, but it also connects us to GE Aerospace and to the mission of our company as well. How that looks in practice, every 2 seconds, somewhere around the world, an engine or an aircraft is taking off with our technology on wing. That amounts to 3 out of every 4 takeoffs. And you could only imagine how many planes have taken off since even just the start of our presentation here today. It's a really big number. And that speaks volumes when you look at that last figure there. So at any given moment, roughly 900,000 people are flying around the world, relying and depending on our technology to bring them home safely. So that, again, that hits at that extreme sense of responsibility and respect we have for that purpose statement I was able to share with you all. Now, shifting a bit, that since we've covered GE Aerospace from a company standpoint, we'll dive into our Redshift journey here. And before I get into it, I have had the privilege of speaking a couple different years in a row at different parts of our journey into the Redshift platform. So we moved from on-premise to the cloud, and now what I get to talk about today is how we've continued to evolve our footprint in the cloud, and we've continued to evolve to meet the demands of our end users. And really, when you look at that evolution, it was prompted by making sure we were delivering right for our customers and for our consumers of data and analytics across the business. So I put together a couple of these, what I'm calling modern demands. I don't believe these are unique to GE Aerospace. I think looking around the room, we all experience these demands of our data and analytics systems. But these were the demands that specifically made us think different and made us continue to scale differently with Redshift. The first one has to do with just growing and increasing demand every day. So 175,000 or more queries amounting to 20,000 or more users and any given day, asking for analytics and asking for query access to our main environment here. And that's only growing. New workloads, new use cases, new customer groups every day, looking for more out of our systems. In addition to that, as you can imagine, in an aerospace industry, we deal a lot with things like flight reports. Flight reports happen to look a little different on a cluster. They're really wide tables, they're really deep tables, and they have to process and live right alongside your traditional or your legacy analytics that were much narrower and much shorter. And so we need a system and we need an architecture that can handle both workloads simultaneously and still deliver the output to the customer. And all while the latency windows and the time that people expect these workloads to run continues to shrink. So things that were okay to be running for a day a couple years ago, maybe an hour a couple of months ago, we expect that in the next few weeks we may get an email saying we want this in a matter of minutes. So we need to keep evolving and keep supporting those shrinking latency windows. The other thing is, once we got to the cloud and once we had this fully cloud-native enterprise warehouse, we realized that scaling looked different. We couldn't just scale up with one cluster and meet the demands of every workload across our business. So what we had to do is think different, start thinking in terms of scaling out. And we saw this by listening to our customers, looking at metrics, which I'll cover in more detail later, and realizing that our queue times and the time it was taking for queries to process through a single cluster weren't meeting the demands of our business and were resulting in wait times on the cluster, which further resulted in report windows missing their tight time frame. So we needed to account for that. We needed to solve for the business, because when you need a report, you need it on time. So what that meant is we had to keep evolving. We had to keep thinking different and using some of those more advanced patterns from Redshift to account for it. What you see on the screen here is an image that shows that evolution with time. I could tell you it wasn't as simple as the pictures here, but this is the best way to get it on the screen. And so 2014 to 2021, we had that conventional on-prem monolith. Everything operated in one area. It was victim of all the common trappings of that scenario. So competing compute, no isolation, and the fact that in order to scale and meet demand, we had to forecast ahead and over-provision for a period of time. That's an expensive situation to find yourself in. So when we moved to the cloud, the first thing we did is we split apart the writers and the readers, or the data owners and the data consumers. And so we at least eliminated that first risk of data entering the environment, competing with those that were trying to get the value from the environment. And that was beneficial. You can see there, so Q1 21 to Q4 22, that helped us. But even with that, we still saw that there was a way to get better and a way to improve our architecture. And so we introduced that cloud scale-out pattern. And we took two specific workloads off of our shared cluster. We broke them apart into line of business Redshift clusters. And we started to meet customer demand differently by scaling out clusters, not just up one single instance. And then lastly there, you see the cloud data ecosystem. That picture happens to look an awful lot like what Naresh showed earlier with the hexagons breaking apart. This is now that combination of a hub and spoke with a point-to-point or a mesh type of design. So not only do people read from a producer into the environment, we can start making point-to-point connections. So line of business A can share and collaborate directly with line of business B through shared storage. And when you see the pictures, it tells like a great story, but you may ask, like, how did we know, or when did we know it was time to make a change? And I wanted to call out two specific examples. They in their own unique way, made the case for scale and made the case for my team and our platform group to do things differently. The first was a lift and shift critical operations workload. This probably looks like everything you're familiar with. It has tight dependencies upstream and downstream, data coming into the environment with really close latency windows, data being consumed with close latency windows. And it had over 90 SQL functions built up with time that were orchestrated together to deliver the end analytic to the business. And you can imagine that code isn't always documented properly, right? So it had been handed down through years. They needed to make it work. They needed to meet the requirements of their business. And we couldn't ask them to crack it all open and rewrite it. So what we did is we embraced our first line of business cluster to give this team dedicated and properly sized compute resources in such a way where they had no competition with anyone else on a cluster. They could size it appropriately, and they were able to meet their latency windows by doing so. Now, the other example is almost a complete 180. So this is a team that was willing to rethink everything. And so we had a group that was running an on-prem data warehouse that was trying to modernize their entire line of business and kickstart their analytic journey with Redshift at the heart of it all. So that was different. They were investing in the team and upskilling and cracking open code and rewriting SQL. And in doing so, they rethought the whole combination of workloads running on their Redshift cluster. So we eagerly gave them dedicated compute and said, it's yours, have at it. And in being willing to do it different and to think different and invest in the team, they saw huge rewards. They were able to eliminate 50% of their overall objects and 50% of total pipeline time. That's huge. That's less they had to manage. That's being able to meet tighter time windows. And that's also a lower operational burden. And by the way, they were able to do that with a 40% reduced cost compared to what they were running on-prem. So that team became an early friend of ours, and we continue to look to them to see how they're going to continue investing and evolving. So it's important to listen to your use cases, listen to your customers, and make sure that as they're telling you what is on the horizon for them, you're thinking of new ways to meet that demand. Now I want to talk about some of our takeaways because the journey did take a lot of learning along the way. And there were things that were painful at times. You can imagine no one's happy when a report isn't hitting a time window. So some of the things we learned I wanted to have a chance to share back with you all as learnings and takeaways. On the right, again, one more call out to that simple picture of how it started, how it's going. Right? The picture on the bottom represents now what looks like our organization. People collaborating with data, people sharing across teams, and we're very proud of that, and we think that's going to scale right for us. But what it took was all the learnings on the left-hand side of the screen. So we learned from the get-go that you shouldn't just think of it as lift and shift. If you lift and shift into the cloud, you're losing a lot of opportunity and you're leaving things on the table. Now, in doing so, everyone can't just rewrite queries, but you do have to engage with your customers and figure out if there's a way you can tweak your design a bit so that they're not just moving problems from one place to another. The way you do that is by analyzing your workloads deeply. So analyze points of entry into your environment, where data's coming in, and analyze your key heavy consumer groups. So and by doing that, what you start to see is these hotspots that represent where you have an opportunity and where you can attach dedicated compute to make sure that you're scaling and you're growing efficiently. And by doing that, what you do is you unlock the ability for your node count and your node type to be different. And that was huge for us. Like our shared cluster environment needs a really heavy node type, whereas some of these lighter weight line of businesses can get by with a much smaller node type. And so by segmenting these out, you're able to do right by each consumer group, and that's extremely to your advantage from a cost standpoint. And the only way we got there is by measuring things that mattered. So be willing to adopt things like KPIs, monitor your cluster, monitor what's happening in your environment, and find a way to monitor something that matters to your end customer. So we looked at several things throughout the last few years. The ones I have here on the page are some of those that helped us the most see when we were in need of doing something differently. So knowing when there's cluster weight, knowing how many queries in any given moment are either running across your clusters or waiting was really important. And then building a KPI that amounted to like what percentage of any query that executed in the environment encountered any weight whatsoever. Those were really important for us to dive into and to monitor and to make sure that when we saw a problem with those, it meant time for us to take action. The other thing, and it's slightly to a different track here, is find a way to expose back and assess out your cost. That is a learning. It does seem a little different than some of the other things we've talked about here, but in doing that, we encouraged so many good behaviors. So we exposed back and made transparent metrics around query counts, execution time, data scanned, and disk spill. And by doing that, and by assessing out cost based on those measures, we were able to encourage people to refactor their own code, because money talks. So by exposing that and explaining to our customers and educating them how the two are correlated, they went in and started writing better SQL, writing better code that was able to run more efficiently and cheaper with time. So that was a huge learning. We appreciated the partnership with Redshift there, because we made sure that we attached numbers that would matter. Now, beyond the learnings, we've had some reflections. And the first one is something you've heard me say time and time again, but just scale does look different in the cloud. Don't just think one cluster up, always think many clusters out. Or at least for us, it was think many clusters out. And the way you get there is by listening to those trusted customers who are executing workloads. You'll know when you have a problem if you're listening. They have a tendency to call you or email you when things aren't going right. So listen to them and be willing to adopt a new strategy or a new cluster design. The other thing is design your ecosystem. This isn't just one data system anymore. This is an ecosystem of interoperating parts. And if you design it and you map it to your functions of your business, it's a really powerful thing, because it represents exactly how your business is modeled and how your groups collaborate through data. And so by designing that, you have this really powerful system that scales the way your business scales. And from a cost standpoint or from an efficiency standpoint, this is more of an industry term, but we adopted it as well, which is own your base, rent your spike. So by analyzing your workloads, by mapping them to KPIs, by knowing your customer, you know what workloads are running repeatedly, on what clusters, at what time of days, and you can attach a really cost-effective solution to that. You can provision nodes, you can attach reserved instances, you can do right design to encourage the right cost measure for your cluster. But then you always have this opportunity for unpredictable workloads entering your system. That's when you take advantage of things like concurrency scaling in our instance, or what we hope to get to soon here with serverless at GE Aerospace. And that's how you rent the spike through the more advanced tech. And so it's a combination of both that gives you a really efficient footprint. And when we look at it, it's extremely price performant. And so we encourage others to do that as well. Now, looking ahead, we expect a lot of this to continue, and we expect the momentum that we've started here to continue growing. And the biggest point there is around the data sharing. So the fact that this does represent how our teams collaborate and talk to one another is extremely powerful. And so we expect that to continue, and we expect to see benefit with teams understanding they're a data producer versus when they're a data consumer, and start to understand the inherent responsibilities that come with that. It's a really powerful notion. And so we're encouraged by the early signs we see of teams just operating different, knowing that they're a data owner now. It's not all hidden and just happening beneath the surface of one big cluster. And in doing so, those domain clusters or those little line of business clusters or big line of business clusters, they start to reset your gravity. These big data systems tend to have gravity about them, attract users, attract use cases. And when you split them out, you start to see gravity sort of reset, order reset. And we're encouraged by that because we think it makes sense and it's what should happen next for us. And lastly, you've probably heard it enough this week, but we can talk a little bit about Gen AI. We are extremely encouraged with the early Gen AI workloads that we're running at GE Aerospace, just how heavy of a demand they have on this data that's tucked away in Redshift. And our ability to embrace the Redshift and SageMaker Lakehouse play that was announced here this week at reInvent gives us a chance to continue serving generative AI and Bedrock type of workloads with the data that's residing in these clusters, because it's been built up over years and it's extremely powerful and it's extremely important data to the business. So we see the recent announcements as a way that we're going to integrate that data with these advanced production apps. And we saw this as early as 2024. Some of our earliest production Gen AI users immediately turned around and requested data that was sitting in Redshift, or they wanted an agent to reach out and interact with it. So we're encouraged by that as well. And before I finish, I did want to end with a quote here from our VP of Data and Infrastructure Services, Justin Henderson. So the platform demands across global analytics community have never been higher. Adopting Redshift and multi-cluster architecture is key to serving customers today while continuing to scale for tomorrow. And I thought his quote was great. I wanted to end on this because, yes, we're extremely encouraged that this design helped us get to a place where we feel like we're meeting the demands of our customers. But it's even better that we think that this is the way we're going to keep scaling as demand keeps growing. And we don't have to, I don't have to be up here in a year talking about a way that we had to blow everything apart and do it different. So this is going to be how we scale and how we continue to grow our environment. So we're encouraged by that as well. I'm going to hand it over to Anusha, but before I do, I just want to thank, there's a lot of team members here that aren't in the room from GE Aerospace, so I want to thank them. I want to thank all the groups that were working on these scaling initiatives over the years. It's been exciting, and thank you all as an audience. With that, I'm going to turn it over to Anusha, and she's going to do some demos and a bit more content. Thank you.
Thank you so much, Alcuin. Hello, everyone. I am Anusha. I'm a Redshift Specialist SA. We've heard both Naresh and Alcuin talk to you about the challenges with single cluster architectures and the benefits that multi-cluster and scale-out architectures provide to you. In this next segment, we are going to see a demo of it. In the demo, we'll take example of a fictitious retail firm called Any Company. Any Company has 4 business units: sales, finance, marketing, and support. This is representative of most of what you all do in your firms. There are multiple business units, or like some of you have, there can be multiple tenants. Our friend Paul there, he mentioned that there are multiple colleges use the same data warehouse. So there can be multiple tenant workloads like this as well. But this demo is a representation of any workload that has multiple users sharing the same underlying compute. So what you're seeing here is we'll first see the challenges that any company will face if all their business units are using the same monolithic compute, as you can see in the picture here. On this monolith, a lot of things are happening. Sales is ingesting orders data from PostgreSQL database into this monolithic endpoint using a zero ETL integration. For those of you who are not aware, zero ETL instantly replicates data from your source databases into Redshift, and it's continuous replication. Then finance is doing the same thing for finance data, which is invoices and payments are getting loaded into this endpoint using zero ETL integration. Marketing is getting clickstream data from Kinesis data stream using streaming ingestion. And support is loading support cases, customer reviews, all support related data using batch ingestion, which is copy commands into Redshift from S3. All this ingestion is happening. In addition to that, all these business units are loading a common table called Customer 360, which is a consolidation of all the customer interactions that all these business units have. Once this data is loaded, all these business units use a variety of BI tools, data APIs, and data science applications to analyze this data and get insights out of it. So there is a lot of activity going on this one monolithic endpoint. Now let's see how that looks like in terms on Redshift and how this all looks like in terms of metrics and some of the KPIs that Alcuin was talking about. So this is the Any Company warehouse. This is the monolith. And we'll first look at the ingestions that are happening onto the Any Company warehouse. So for that, let's see the zero ETL integrations. You see 3 integrations all going into the Any Company warehouse. The first one is sales data that I was talking about from Postgres. It's continuously replicated. The next 2 are payments data from DynamoDB. If I go into one of these integrations, you can see a variety of metrics. I can see the number of tables that are replicated, the count of rows that are replicated from the source. As the screen refreshes, you see the count keeps increasing, showing that data is continuously being ingested. Similarly, data from DynamoDB is also being continuously ingested into the same endpoint. Now I'll connect to any company's warehouse, and let's take a look at the other data sets as well. First, let's take a look at the marketing, which is getting data from the clickstream. And you can see that stream available as a table called website clickstream within Redshift itself. And on that clickstream, there is a materialized view, which is continuously ingesting data from the clickstream into this monolith. And let's get a count of those rows from that materialized view. And I get a count of this. It's a simple count query from that materialized view. And you can see that it's around 96,500 rows. And you refresh the count increases as the data is continuously ingested from the stream. Then this is the support data set. There is customer reviews, support cases, both the data sets and their corresponding counts for support. In addition to this ingestion, which is unique for that business unit, there is loads happening into the customer 360 as well. And you can see the counts by org, all orgs loading into this. In addition to ingestion, there is a lot of querying happening. So to see that querying activity, we'll query the query history table. It's a system table that you can query and see all the activity for the last 1 hour at the time of that query when I ran. And in the output, you can see that when that query was run, there were 6 queries queued, hundreds of thousands of queries successful in the last 1 hour, and around 28 queries running when I ran that query, which is a lot of activity happening in one monolith. Let's see how this reflects in metrics. Alcuin mentioned one of the KPIs, and we'll see that KPI. Here, any company for the last 1 hour, the running and queued queries, you see a lot of reds here. Red indicates queuing, which indicates resource contention. And now you can go into the details of this cluster metrics. And one of the metrics that you can see is how many queries are completing per second. The query throughput on this monolith right now is around 15 queries per second, and a single bad query can impact it. Here is a bad query, which is joining 5 different tables, no join condition whatsoever, so it will return into a Cartesian product. So when I ran that query, you can see an immediate impact in the query throughput. The query completed per second previously was around 15 queries, right? And you can see that came down to 10 queries per second within just a very short period of time. And that could be the impact that a bad query can have on the overall workload when everything is running on the same endpoint, which can be drastic, right? And we've seen the challenges in this demo with this architecture. There is resource contention. A single bad process can impact the entire workload. And also from a cost allocation standpoint, if you want to charge back each of this business unit for their usage, it's quite challenging. So how do we address these challenges? We address this by re-architecting. And Redshift makes it really easy for you to re-architect it into a multi-cluster architecture because it has compute and storage separation. Now, after the re-architecture, you can see that each business unit gets their own endpoint. Sales has their endpoint, marketing, finance, support all have their endpoints. And now you have the flexibility to size them based on their unique requirements. You can see support got more compute, 64 RPUs. Support is doing batch ingestion, and it is running heavy queries, so we gave it more compute. Whereas look at marketing and finance, they're at 16 RPUs, smaller compute. They're doing low latency ingestion, and they do not have heavy queries, so smaller compute suffices. And all these endpoints are ingesting their own data sets using their own compute, and they will continue to have the ability to write into the common customer 360 table. Because compute and storage is separate, but still you have the ability to write into common data sets from all these computes together. Now let's see how this looks like on Redshift. After re-architecture, you see those 4 new endpoints created, one for each business unit. It can be one for each of your tenants as well. These are those endpoints: sales, marketing, support, and finance. And the zero ETL integrations, which were now previously loading into the same endpoint, now load into their own, using their own corresponding endpoint. So here are the updated ones. You can see that finance data from DynamoDB is now going into finance namespace, and sales data from PostgreSQL is going into the sales namespace. Similarly, marketing data is going into the marketing namespace, support data sets are going into the support namespace, so on and so forth. Then Naresh spoke to you about this new capability that multiple computers can write into the common data sets. Now let's see that. We spoke about Customer 360, it's a common data set. How can multiple endpoints write into that common table? We'll see that using this piece of the demo. Each of the 4 boxes that you're seeing on the screen, they're connected to each of the 4 business units we're talking to you about. Left top is sales, then is finance, then marketing, and then support. Now let's assume that Customer 360 table was first created by sales. And currently this table is empty and only sales has access to it. Now sales can give access on this common table to all the others using just 2 simple steps. One is create a data share which has this Customer 360 table which has insert privileges on it. Those 2 sequences done. And then sales grants access on this data share with the all other business units. With finance, with marketing, with support, just grant usage. With those 2 simple steps, sales has given access to the other endpoints to be able to write into this common table. On the consuming endpoints, which is on finance, in marketing and support, all you would do is create a local database instance that is pointing to this data share. And once those local database instances are available, you can use any load mechanism of your choice. Here I'm using a copy command, which is a bulk load mechanism. You can use inserts, you can use any other insert mechanism to load the data into the table. You see all these copy commands are loading into the same table simultaneously, concurrently loading. And as soon as the loads are completed, as you can see on the screen, you can see that the loads are getting completed. And when the load is complete, all other endpoints can see the data with transactional consistency. Here, if I run that query from the sales endpoint, as soon as the loads are complete, you can see the data available in here. So like that, all your ingestion is isolated. Every business unit is performing ingestion of their data assets in a completely isolated manner. What you have seen in this part of the demo is Redshift to Redshift data sharing. Naresh was talking to you about how you can do all of this in a centralized manner using lake formation, right? So let's see how that is done now. So let's take this example now. Sales has their data tables. Now what sales want to do is give permission on the sales tables to finance. They want to give, there is a table called customer that finance also needs. So how can they achieve that? So what sales will do is what you can see in the demo here. Sales will go to its namespace and just say publish to data catalog. The data catalog can be within the same account. It can be in a different centralized account. And once it is published, an admin can go into the lake formation catalog and they see a request which they approve and they create a catalog. Here we are calling it sales catalog. And to this catalog, you attach an IAM role with appropriate privileges and just create the catalog. Once that catalog is created, all the sales tables can be seen under that catalog. And there is the sales catalog, and you can select that and you say view tables, and all the sales tables will be visible. Once the catalog opens, you can see here orders, customer, line items, and you can choose customer table here and then grant privileges on this customer table. I'm giving privileges to finance analyst here. Finance analyst you can give access for the entire table, you can choose individual columns, individual rows, you can do fine-grained access control. And once that grant is successfully done, I log in as a finance analyst into Redshift, and let's see what the finance analyst can see. Finance analyst has access to finance work group, right? So they log in as a federated user, and as soon as they log in without any additional setup, they can see the sales database and the customer table that they have been given access to. With just those simple steps, publish the entire namespace to catalog, do permission management using lake formation, and grant access on that business unit's data assets to whoever needs to get access to. This way, each business unit can control who can see what, and they can adhere to their compliance needs in order to share their data assets, right? Now, with this updated architecture, a single bad query on one endpoint is not going to impact others because their compute is completely isolated. The blast radius is also much smaller. The impact of bad processes is only isolated to that particular endpoint, and that can be sized. Each endpoint can scale up, scale down, based on their unique requirements. In addition to that, you have now let's see the metrics after this isolation is done. Here is how the metrics look like. Previously, if you remember, there were a lot of reds in this graph, and now you hardly see any reds on the graph, showing the resource contention has significantly reduced. And each of these endpoints can be tagged to their cost center, and you can just simply charge it back to that cost center, right? So let's see that. Now, after tagging, you go to Cost Explorer. For each of the business unit tag, sales, finance, marketing, and support, there is a separate cost that you can allocate to that business unit very simply and do cost allocation. Let's bring this all together. As a summary, here are the best practices when you're architecting Redshift for multi-cluster architectures. Create a separate endpoint for each of your workload or for each of your group. Size that endpoint based on that workload's unique requirements. If you use serverless, it becomes very easy. You can use AI-driven scaling, which will automatically determine the size of that endpoint for you. And then use Lake Formation for centralized data governance and permissioning management. Some of you have indicated that you use single cluster architectures, or we have seen some customers start simple, where they start one endpoint and do all the processing within that. If you start like that, or if you're already in a single cluster architecture, let's see how you can convert that into a multi-cluster architecture. For that, let's go through a process flow. It has 4 simple steps. What you're seeing is an example of a single cluster architecture, which with 4 typical workloads that we see in the data warehouses. There is an ETL workload, there is reports, data science, ad hoc querying, all running on the same endpoint. Now let's see how you can convert this into a hub and spoke architecture. So the first step is perform a snapshot and restore for each workload or each group. Here there are 4 workloads. ETL will remain on the hub. Now for the other 3 workloads, which are your reporting, dashboards, and data science, you perform a snapshot and restore. So you have now 3 separate endpoints. Next, repoint your consuming applications from your monolith to each of the separate endpoints that you have created. And once that is done, drop any unrelated schemas from these endpoints that you may have. And there you see hubs is ready, now spoke is ready. All you need to do last step is share the data from ETL, which is your hub, to the consuming endpoints. With those 4 simple steps, you can convert a single cluster architecture into multi-cluster architectures. Here, we want to give you some blogs that you can refer to later. To learn more about multi-cluster architectures, I'll pause here for a couple of seconds so that you can take pictures of this, and you can refer to these blogs later. Awesome. I see some of you are still taking pictures. All right. So that's about the talk. Thank you all so much for attending this session. Please take some time to complete the survey on the app, and we are really happy to be presenting this content for you, and we are happy to take any questions that you may have for us.